Welcome back. And next paper before the WAKE will be presented by Dr. Datta and it's about WAKE-INDUCED FLUTTER of two-way tapering always in a very straight rudder in non-uniform propeller beam state. So let's wait for the music to finish and then thank you.
Thank you, David. Namaste, good afternoon, hello. I'm Dr. N.Datta from Indian Institute of Technology, Kharagpur, India. And I'm here to present my paper titled WAKE-INDUCED FLUTTER of two-way tapered hollow marine spade rudder in non-uniform propeller slipstream. This work has been done with the help of my BTech student, Mr. Rahul Jindal, who is now an assistant surveyor in the Indian Register of Shipping, Mumbai. So as I said, this is the title of my talk. I mainly look at a spade rudder, and we have been talking of underwater noise since morning, but this is not about noise, this is about dynamics of the structure. I'm looking primarily at the dynamic behavior of the structure behind the propeller slipstream, which is basically I'm investigating propeller-induced vibration. Sorry. Okay, yeah, this is the contents of my talk. Introducing the geometry, the problem formulation, the analysis. This is primarily a theoretical work backed with some experimental results and some numerical studies. We'll go through that. So introducing the non-uniform wake behind a rudder, behind a ship due to propeller slipstream causes dynamic loading on the rudder as well as the other structures behind the propeller like the stern overhang, leading to detrimental rudder vibration. The frequency of the PIV, propeller-induced vibration, is the shaft frequency into the number of blades of the propeller. So theoretical analysis of the free, dry and wet vibration of a trapezoidal spade rudder is presented here. The rudder is modeled as a hollow Kirchhoff's cantilever plate with the chord section as a NACA 0018 profile and the span section as a linearly tapered cantilever beam. There's a geometry of the spade rudder where we find that the cross-section in the chord-wise direction is a NACA profile. The taper ratio, as we see at the top, the chord length is 6 meters. At the tip, it is 5 meters. The taper ratio is 6 by 5, 1.2. We have the pivot at the top, which is 35% from the leading edge. The material is mild steel, and we know its properties. Now the rudder is hollow, and it has a sheet thickness of 30 mm. Now because it is hollow, should it be a Kirchhoff's plate or should it be a Midland's plate? The family of problems that we have solved is we have looked at the free dry vibration of this plate, wet vibration, and then forced wet vibration. Numerically, we have done the free dry vibration with ANSYS. Some experiments also I'll be talking about, which was done after the paper was submitted in February 2015. So if we take the chord-wise section of the rudder, we have this NACA profile, which we can consider as a free beam. That means the shear force and the bending moment are 0 at both the ends. But it's a non-uniform beam, which means the thickness is varying along the length. In the span-wise direction also, it's a non-uniform beam, but it's very slightly tapered. The boundary conditions remain the same. The shear force and the bending moment are 0 at the ends. If you see the symbol capital Phi, Phi stands for the mode shape in the respective directions. Mode shape, which would mean the natural spatial configuration in which a structure is supposed to oscillate. So combining these mode shapes, we get the plate. This is how the rudder would look like. We consider it as a Kirchhoff's plate, which would mean it's a combination of Euler-Bernoulli beams. Had it been a Timoshenko beam, the combination would generate a Midland's plate, where shear deformation and rotary inertia are taken into account. Euler's beams are thin beams, which would mean that the thickness to length ratio must be less than 1 by 20, 0.05. In the span-wise direction, we have already satisfied this, but in the chord-wise direction, we are not satisfying. Here, we need to be a little careful. Why? Because it's a NACA 0018 profile, meaning the maximum thickness to the chord length is 0.18, which would mean we are at a thickness to length ratio greater than 1 by 20. So what do? Do we consider the shear deformation? As of now, we are not considering because remember we have a hollow cross section, which would mean that the shear deformation at the 30 mm thickness sheets, they are quite small, and therefore the rotary inertia is also ignored. So therefore, as of now, we have Euler-Bernoulli beams in both span-wise and chord-wise directions, combining which we get a Kirchhoff's plate. So looking at the beam vibration first, we have the standard equation for beam Euler-Bernoulli beam vibration, but because it is non-uniform, we cannot be having the standard mode shapes of a free beam. We have to combine free mode shapes, weighted combination, to generate non-uniform beam mode shapes. Uniform beam mode shapes are well known, they are closed form solutions, but non-uniform beam mode shapes has to come out from the energy-based Rayleigh-Ritz method. And the non-uniform beam mode shapes are not orthogonal to each other. Orthogonality would mean that when we integrate mode shapes, phi1 first mode shape into phi2, we integrate over the length, we get a 0. So phi j into phi k integration dx is 0 only if j is equal to k, it's not equal to 0. Okay, so minimizing the potential energy, a system is predisposed to vibrate at its natural, at the minimum energy configuration. Minimizing the energy, we get the natural frequencies, but we are not interested in beam-wise natural frequencies because we are interested in the rudder frequencies, which is a plate. So why are we doing beam vibration? In order to get the non-uniform beam mode shapes, which will later be input into the plate vibration equation to do the plate vibration analysis. So we do this beam vibration analysis with the Rayleigh-Ritz method in both the directions before we proceed to the Bellerking's method to solve the Kirchhoff's plate equation. This is the well-known Kirchhoff's plate equation where we have dx, dy, dxy, the coefficients, they are the bending stiffness in either direction. dxy is the twisting rigidity of the plate. The total displacement, capital Z, as a function of space and time, is considered to be a superposition of the plate mode shapes capital Phi and Q, which is the time-varying principal coordinate. Using separation of variables method and applying the Bellerking's pre-multiplier, we can convert this problem into an eigenvalue problem from which we get the eigenvalues, the omega, which are the natural frequencies, and the eigenvectors, which are the weights. This eigenvector, if we go back, this eigenvector comes in here. It multiplies with the product of the beam mode shapes, and the S is the span-wise direction non-uniform beam mode shape, and C is the chord-wise direction non-uniform beam mode shape. A combination of this with the weighted combination generates the plate mode shape in the X and the Y directions. Now, why do we need the plate mode shapes? Because a combination of them will give the total dynamic behavior of the rudder behind the propeller slipstream. Okay, once we have done the dry vibration analysis, that means the dry vibration frequencies are known, we should look at the wet vibration also because mostly the rudder is acting underwater. So definitely we have to look into the fluid inertia associated with the vibrating body. So first we do it by the two-dimensional approach where we have, suppose we take a chord-wise section and applying strip theory, we get the two-dimensional pressure as this. Here the psi that we see is the two-dimensional velocity potential associated with the two-dimensional aerofoil section. This velocity potential satisfies a boundary condition at the interface between the rudder and the water, which is the no penetration boundary conditions. Once that is satisfied, we will be able to find out the added mass of each strip along the chord-wise and then add it up along the span of the rudder to generate the total added mass, and therefore we can get the net natural frequencies. However, strip theory is valid for longish kind of bodies. We find that the length of the rudder is 10 meters and the average chord length is 5.5. So it's more a squarish kind of a structure. So we should go into three-dimensional Green's function technique, which we have done to generate. This is the three-dimensional pressure, linear hydrodynamic pressure, where phi is the three-dimensional radiation potential. Again, it satisfies the boundary condition at the plate surface. The del phi by del z is the fluid velocity at the interface where z is equal to 0, that's the surface of the rudder, that matches with the structural velocity at that point. This boundary value problem is solved numerically using the 3D constant strength source distribution technique. Now, once the free vibration is done, let's look into the forced vibration. Let's see what the hydrodynamic force is on the rudder. The propeller slipstream causes a hydrodynamically varying load on the rudder, whose spatial distribution has been calculated empirically for 5 different rudder angles. The rudder works at different angles depending on how we are maneuvering it. So the loading on the rudder acting behind the propeller, that changes. And how does it change? It depends on the angle of attack alpha, the aspect ratio of the rudder, drag coefficient, center of pressure, the center of pressure, and this has been calculated by the Harrington's empirical formula. The variation of the lift coefficient, which is acting normally on the rudder over the airfoil section, is taken parabolic with the maximum at the mean chord. Parabolic means over the span length it's parabolic, and over time it's oscillating. The normal force coefficient and external hydrodynamic forces are calculated again by empirical formula. So the forced plate vibration equation, now we have this standard equation for the plate, which I talked about in the free vibration, and now we have the external fluid loading on the plate. This fluid loading has been calculated empirically, as I spoke about, and it's varying with respect to time at the frequency omega VI, it should be PIV, I'm so sorry. PIV would mean propeller-induced vibration, and the frequency of propeller-induced vibration is the shaft frequency into the number of blades of the propeller. So we get the coefficient of normal force on the rudder. Cn is the coefficient of normal force, which depends on the lift coefficient and the drag coefficient, and alpha is the angle of attack of the flow on the rudder, depending on the rudder angle. So when we solve this equation by modal superposition, we can get the stresses generated in the Kirchhoff's plate, sigma x, sigma y, and tau xy. Sigma x and sigma y are the bending stresses in the x and the y direction respectively, and tau xy is the twisting stress. Now, looking at the results, we have first the chordwise mode shapes. Now, what do we see here? We see some dashed lines, which are the uniform beam mode shapes of a free beam. But because of the non-uniformity of the NACA profile, the NACA 0018 profile, because of the non-uniformity, we find that the Rayleigh-Ritz method gives us non-uniform beam mode shapes which have deviated considerably from the uniform beam mode shapes. But in the span-wise direction, we find that the deviation is not so much. The reason being that the taper is mild there. It's quite a mild taper. So the blue one is the first mode shape, the red is the second, the green is the third, and so on. And each one corresponds to a higher natural frequency. But we are not interested in beam-wise natural frequencies. We look at the plate natural frequencies and associated mode shapes. So if this is the rudder, which is trapezoidal in shape, we get the first bending mode shape as this, which is a combination of the first mode shape in the span-wise direction and the